Hi everyone, so continuing our Tech Master series, let's try to solve this problem. So here you need to find the value of V0 and Vx for Vin equals to 2 volt and Vin equals to 6 volt. Now if you see the question, you will say this is very basic question and we have solved this kind of question in the gate examination. So what is new here? Okay, you have solved, I know, but let's watch the video till the end, you will learn certainly a lot of new things. So yeah, when Vin is 2 volt, what will happen? When Vin is 2 volt, what will be the output? Output is simply V0 is equals to minus Vin. So when Vin is 2 volt, what will be the output? Output will be minus 2 volt. And what will be the Vx value? Vx value will always be 0 volt. Why so? Because virtual short is valid. Virtual short. Moving on to the second one. When Vin is 6 volt. So if Vin is 6 volt, what will happen? How do you solve it? When Vin is 6 volt, what should be your output? Output should be minus 6. But that cannot happen because the saturation voltage is minus 5 volt. So output will reach up to minus 5 volt only. So your output will be minus 5. Right? So when V is 6 volt, your output wanted to go to minus 6 volt, but it cannot go there. So output will be minus 5 volt. Right? And based on that, what will be your Vx value? Because your output is minus 5 now, what will be your Vx value? So Vx value is simply, you can apply nodal analysis, or I have told you one rule. I will tell once again. This is R1, this is R2, this is V1, this is V2. If we need to write the potential of this point, let's call this V3. What will be V3? V3 will be V1 into R1. Sorry, let's call this as R2. So it would be V1 into R2 plus V2 into R1 upon R1 plus R2. So similarly, what you can say here, what will be the potential of Vx? V0 into R plus Vin into R by 2R. So simply Vx would be V0 plus Vin by 2, right? So from here you can get the value of Vx, that would be V0 is minus 5 and Vin is 6. So minus 5 plus 6. So from here you get to know that Vx value is 1 by 2. Very easy. V0 value, this is by 2 is 4 V0 plus Vin by 2. This is the thing. So V0 is minus 5 and Vin is 6. So minus 5 plus 6 by 2. That means 1 by 2. So this is your Vx value. This is the approach, but is that the approach you are going to give to the interviewer? No. Let's check something different. Let's see something different now. So I will draw the same circuit. I can copy it only. Now forget about V in value, forget about anything. Tell me one thing. Let's assume I am assuming the gain to be A. I know gain A is infinity. This I know, but I am just assuming gain to be A. So one equation I can write, V0 is equals to AVX. Are you agreeing with this point? V0 is equals to AVX. Now I am drawing the graph between V0 and Vx. V0 versus Vx. V0 at y-axis and Vx at x-axis. How will the graph look like? When Vx value is positive, what will be V0 value? Just look the OpAmp as a comparator. Just look at the OpAmp as a comparator only. So what happens in comparator? When the negative potential is higher, what will happen? The output will be negatively saturated. So this will be the waveform, right? Forget about negative feedback or anything. I am just asking you to look at the OpAmp as a comparator only. And if Vx value is negative, that means this value is negative. That means V positive is higher. So output will be positively saturated. So if Vx is negative, my output will be plus Vsat. And if my Vx is positive, my output will be minus Vsat. Are you agreeing this point? So this is the first equation we wrote. From that we made the graph. And this point is Vsat. Instead of that, we should write plus 5. and here we should write minus 5 volt. Now one more equation we can write. What is the equation that we can write? Vx equals to V naught plus V in by 2. How did you write? V in into R plus V naught into R by 2R. V in into R plus V naught into R by 2R. So Vx would be V naught plus V in by 2. So from here we need to find the relation between V naught and Vx. So what we can write? V naught is equals to 2Vx minus V. This is the equation 2. V naught equals to 2Vx minus V. Now I am putting the value of V in one by one. First I will put V in equals to 0 volt. If V in is equals to 0 volt, what will be the graph? V naught equals to 2Vx. So how will the graph look like? Let's use this color of pen. When V in is equals to 0, V naught is equals to 2Vx. Simply this is how the graph will look like. Although the slope looks like 1 here, but you need to assume it is 2. So this is for V in equals to 0. When V in was 0 volt, this is how the graph would look like. Agreeing with this point? Let's assume your V in is 2 volt. If V in was 2 volt, what will be your output? That would be 2Vx minus 2. That means it will cut y-axis at minus 2. It will cut y-axis at minus 2. This. The slope is the same. Slope is plus 2 only, but now it will cut y-axis at minus 2. छींक आ गई थी थोड़ी सी. So it will cut y-axis at minus 2. And the slope will be same. So the line will be parallel only, but it will cut y-axis at minus 2. So this was for V in equals to 2 volt. What if I was asking for V in equals to minus 2 volt? What would be the graph? V naught equals to 2Vx plus 2. So it will cut the y-axis at plus 2. It will cut the y-axis at plus 2. So this is the graph for V in equals to minus 2 volt. What do you see here? What is the operating point if you study analog electronics or simple mathematics as well? Like, let's assume I am giving you two equations, y equals to x plus 2 and the other equation is y equals to 2x plus 1. These two equations I am giving. Then how will you find the solution of these equation? You will make two graphs, y equals to x plus 2. This is the graph, and then y equals to, let's assume this is minus 2x plus 1. So minus 2x plus 1, this graph. And where the graph cuts, that is the operating point. From here you can get the value of x and y. Are you agreeing to my point? Now I have made two graphs between V0 and Vx. And where my graphs are cutting, for V in equals to 0 volt, this is where my graph is cutting. Tell me at this point what is the value of V0 and Vx. Both values are 0. At this point, when V in is 0, I am studying the graph only when V in is 0. So the graph is cutting at this point, where both Vx and V0 are 0. Now where my graph is cutting? At this point. For V in equals to 2 volt. For V in equals to 2 volt, what is the value of Vx here? Again it is 0. Right? The value of Vx is again 0 here. What is the value of V0 here? We actually don't know, but that would be minus 2 volt. Check for this point. Value of Vx is again 0 here. And what is the value of V0 here? That is plus 2 volt. So what can you see here? That no matter whatever the value of V in you are taking, the graph is always cutting at Vx equals to 0 only. That's why virtual short is valid here. Now we will see for positive feedback as well, but let's check for V in equals to 6 volt. Now we will see, after that we will see for positive feedback. Then you will realize why in positive feedback virtual short is not valid. You will see with the nature of graph. But let's check for V in equals to 6 volt. Why at V in equals to 6 volt virtual short is not valid? Like when V in was 6 volt, we did not say that Vx is 0 volt. We said that output is saturated, that means virtual short will not be valid. So why is it so? Let's understand by graph. So if V in is equals to, so let's write, where should we write? On the next page. Okay, on the next page only we will write, when V in is equals to 6 volt, what will happen? What will be my output? 2Vx minus 6 volt. That would be 2Vx minus 6 volt. That means it will cut the y-axis at minus 6 volt. It will cut the y-axis, and this should be increased. It will cut the y-axis at minus 6 volt. Now where will be minus 6 volt? Somewhat below this minus 5. Somewhat below this minus 5. So the graph will go something like this, because it will cut below it, because from here we can see what is our equation, 2Vx minus 6. That means it will cut the y-axis at minus 6 volt. So minus 6 volt will be somewhere here. So now where the two graphs are cutting? The two graphs are cutting only at this point. This is the point, and at this point your V0 is minus Vsat. And what is minus Vsat? Minus 5. So the graphs are cutting at this point. So at this point your Vx value is, this is your Vx value. This is your Vx value. At this point your Vx value is half and your V0 value is minus 5. Although we don't know how it is half because we have already calculated it previously, but if we had made it on the real paper, we could know what will be the value of Vx, and also V0 value we can directly see, that is minus 5. So here we can give the explanation why virtual short is not valid, because when we made the graph, it cut on the saturation point only. In the previous one, when Vin was 0 volt, 2 volt, minus 2 volt, it was cutting on the, when Vx was 0. It was not cutting on the saturation point. They are the saturation point. The graph was not cutting here. The graph was cutting where? When Vx was 0 volt only. But here the graph cut when Vx is half and V0 is at saturation. Are you getting this point or not? So it is cutting at this point. So this is the point. This is the operating point. That's why when Vin is, what was Vin here? When Vin is 6 volt, your virtual short is not valid. The same thing will be happening for Vin equals to minus 6 volt. So when Vin will be equals to minus 6 volt, what will happen? The graph will cut somewhere here. The graph will cut somewhat like this when Vin equals to minus 6 volt. Are you able to grasp this point or not? This is a different explanation of virtual short. This is virtual short only, but the correct and different explanation. What did we do? We wrote two equations. V0 is equals to AVX. The graph would be this, and Vx is positive, output will be minus Vsat, and Vx is negative, output will be plus Vsat. And then we wrote one more equation. Vx is equals to V0 plus Vin by 2. So from there we got to know V0 is equals to 2Vx minus Vin. Now we are putting Vin equals to 0. So V0 is equals to 2Vx. So this is the graph we are getting. So here we got to know this is my operating point. That means V0 and Vx both are 0. When Vin is equals to 2 volt, this is the graph I am getting, 2Vx minus 2. So here my Vx is certainly 0. Vx is 0 only. This value, Vx is 0 only here. But my V0 is minus 2. So here my output will be minus 2 volt and Vx will be 0. Virtual short is valid here as well. But when I am putting Vin equals to 6 volt, what is happening? My output is 2Vx minus 6. That means the point at which it cuts on y-axis, that will be minus 6. Somewhere here. That means it will cut the graph on saturation point. So here it is cutting the graph on saturation point. It will cut V0 versus Vx graph on saturation point. That means output is saturated and Vx is this time not 0 volt, it is 1 by 2. That's why virtual short is not valid here. And in positive feedback, virtual short is never valid. Why so? Let's check that in next slide. So I hope you have understood this slide, why I put this question, because this was very straightforward. We have solved this kind of question in GATE, but this is how we solved. But here we needed to build a different approach, right? So in the interview, if you solve the question like this by making the graphs, then they will be highly impressed, because 99% of the students are going to solve like this. But this is not the approach they would want from you, right? Because they are thinking as a designer, not like a problem solving skills. Like they certainly know you have problem solving skills because you have cleared the GATE, but they want you to think as a designer. They will certainly give you a hint to think like that, and if you have studied it, you will be able to think very quickly. Now let's do the same analysis for positive feedback. First we will do what you have already studied. So basically we have to analyze this circuit. So how you have studied? You have studied it as a Smith trigger. So how do you solve Smith trigger? In Smith trigger, we always assume any output. You can assume any output. You can assume plus 5 volt or minus 5 volt, because we already know that output will be saturated at plus 5 or minus 5 only. But why it will be saturated, that I will tell you later on. But let's solve it in a general way. So how do we solve it in gate? So what do we do? First we assume our output. We say that let's assume V naught is 5 volt. Take V naught equals to 5 volt. After taking V naught equals to 5 volt, what we do? Now we try to make V naught equals to minus 5. So at what condition my V naught will be minus 5? This is what we try to do. So when it will be minus 5? When Vx is less than 0. When Vx is less than 0, my V naught will be minus 5 volt. So what is Vx? Vx is V naught plus V in by 2. V naught plus V in by 2 is less than 0. What is my current V naught? Current V naught is plus 5 only. So plus 5 plus V in by 2 is less than 0. So when V in is less than minus 5, my V naught will be minus 5. So basically, how will the characteristics look like? This is V naught, this is V in. What did you assume first? Whatever that you assumed, from there you need to start. You assumed output to be plus 5. And what was the point where it was changing? The point it was changing was minus 5 volt. This was the point where it was changing. So first you assumed your output to be plus 5. So you assumed your output to be plus 5. So from here you will start. I assumed my output to be plus 5. Now it is going to minus 5. Now it is going to minus 5. So you are going from plus 5 to minus 5. So where will be your arrow? Like this. You won't make your arrow like this. You are not going from minus 5 to plus 5. You are going from plus 5 to minus 5. So that's why my arrow will be plus 5 to minus 5. This is how my arrow will be. And this is my value of V in. It can vary from anywhere. So what does this graph tell? This graph tells that if I am moving from minus infinity to minus 5, my output will be plus V set. That is equals to plus V set, that is equals to plus 5 volt. If I am moving from, if my input is moving from minus infinity to minus 5, my output will be plus 5 volt. And if my input is moving from minus 5 to minus infinity, my output will be minus 5 volt. Now, if I say my input is moving from, you need to hear it. If I say my input is moving from 0 to infinity, what will be my output? You will say, I don't know. I need to make another graph. By using this graph, I can't tell what will be my output if I am moving from 0 to infinity, because this graph tells only moving in the left hand side, only moving in left direction. You are moving from 0 to infinity, that means you are moving in right direction. That this graph cannot tell. So for that you need to make another graph, and there you will assume your output to be minus 5. So the same analysis you will do, and what you will do, you will assume output to be minus 5. Assume my V naught is minus 5. Now you are moving from minus 5 to plus 5. So my V naught is minus 5. So when this will go down, when Vx is greater than 0. When Vx is greater than 0, what will happen? My V naught will be plus 5. When Vx is greater than 0, my V naught will be plus 5. What is my current V naught? Current V naught is minus 5 only. So this equation I can directly write minus 5 plus V in by 2 should be greater than 0. That means V in should be less than 5. So when V in is less than 5, my V naught will be plus 5. Is that so? Is there something different? When Vx is greater than 0, my V naught will be okay. And minus 5 plus V in by 2. So when V in is less than 5, my output will be my output will be plus 5. Yeah, sorry, it will be greater than. When Vin is greater than 5, my output will be plus 5 volt. So again you can make the graph V naught versus V in. V naught versus V in. So V naught versus V in. What is the point? That point is plus 5. Now you are moving from minus V set to plus V set. So basically your output is minus V set, and then you are moving from minus V set to plus V set. So this is how you are moving. Minus V set, that is minus 5 volt to plus 5 volt. So the arrow is like this. Now based on this graph you can say what will happen if my input is moving from 0 to 5 volt. If my input is moving from 0 to 5 volt, my output will be minus 5 only. And if my input is moving from 5 to infinity, my output will be plus 5. So based on both of the graph, we can make one graph using both of them. So two graphs were there. First one was this, where we were moving from plus 5 to minus 5. And then the second one was this, where we were moving from minus 5 to plus 5. This is minus 5 volt, this is plus 5 volt. This is V in, this is V naught. This is plus 5, this is minus 5. So in the first graph, that this was the scene. This is the arrow for the first graph. And what will be the arrow for the second graph? For the second graph, the arrow will be something like this. You are moving in this manner, minus 5 to plus 5. So are you getting this point? Now, if someone says my input is 6 volt, what will be my output? Someone is saying my input is 6 volt, what will be my output? It will be 5 volt only. It is fixed. If my input is 6 volt, my output will be 5 volt. That's for sure. No one can deny that. Now, if someone says my input is 4 volt, what will be my output? You will say I can't tell, because you are in the dead zone. This particular area is known as dead zone, because here both of the output are possible. Your output can be plus 5 volt as well, minus 5 volt as well. It depends from where to where you are moving. If you say my input is 4 volt, but I have moved from plus 5 to 4. My input is 4 volt, but I was moving in the left hand direction. That means I was going from plus 5 to 4. So what will be my output? My output will be plus 5 volt. Why so? Because you are moving in this direction and the arrow shows in this direction only. If they say my input is 1 volt, what will be my output? You will say I can't tell, sir. Why so? Because you are in the dead zone. You need to tell me from where to where you are moving. Now I say that I am moving from 0 to 1 volt. So at 1 volt, what will be my output? I am moving from 0 to 1 volt. So at 1 volt, what will be my output? So you are moving from 0 to 1 volt. 0 to 1 volt in this direction. That means this graph will be followed. So my output will be minus 5. Are you getting this point or not? So this is how you study a hysteresis curve. This curve is known as hysteresis curve. So this is how you study a hysteresis curve. In a lot of written paper, I have seen this kind of hysteresis curve and they ask you questions from that. And guys think that it is impossible to solve, but this is not impossible to solve unless you know the meaning of hysteresis curve. We study Smith trigger, but we never know the meaning of hysteresis curve. Now I hope you have understood the meaning of hysteresis curve. Hysteresis curve just simply tell your output only, but with the direction from where to where you are moving. So in a Smith trigger, in the given circuit, if your input is moving from minus infinity to minus 5, minus infinity to minus 5, that means your output will be plus 5, and if it is moving from minus 5 to infinity, your output will be minus 5. And if your input is moving from plus infinity to minus infinity to plus 5, that means your output will be minus 5, and if input is moving from plus 5 to infinity, that means your output will be plus 5. Got that point? Got the simple analysis of Smith trigger? But this is something that you have studied in GATE, but now I will tell you something different. But I know a lot of guys must not have studied it in GATE as well, because I know teachers don't teach that much of things in the GATE, but should be taught. Yeah, so now you have understood the meaning of Smith trigger as well. You have understood the meaning of hysteresis curve as well. You also know how to draw the hysteresis curve. Now let's solve the circuit with the simple analysis. And we will also verify the dead zone. We will also verify this zone, this one. We will also verify this zone as well. So let's make the circuit once again. Just copy it and we will solve this circuit with the simple graph. Those graphs we made here by these graphs. And we will also understand why in the positive feedback virtual short is not valid. So these 30 minutes videos only will make you learn a lot of new things. And I hope you are watching the previous videos as well of transient analysis. Once you go through those videos, you will realize there are a lot of things which you don't know. I'm not saying that you don't know anything, but still there are a lot of things which I have taught, and in GATE industry these are not taught, but they are valuable. IITs can ask question from that anytime. And certainly in the interview you are going to face those questions which I have covered in that RCRL playlist. So you need to watch those videos. Please do watch those RCRL videos, because that is very important. All those OpAmp questions will come later on. First you need to answer those RCRL videos. Okay, so yeah. So here we can again write the equation V naught is equals to AVX. Okay, previously I wrote V naught equals to AVX, but it should be minus AVX. I'm sorry for that. V naught equals to minus AVX, because here negative sign will be there, no? Yeah. So here what we can write, V naught is equals to AVX. My V naught is AVX. So how will the graph look like? If Vx is positive, that means my output will be plus 5. If Vx is positive, that means my output will be plus 5. And if Vx is negative, my output will be minus 5. Are you agreeing with this point? Are you agreeing with this graph? If Vx is positive, my output will be plus 5 volt. And if Vx is negative, my output will be minus 5 volt. Right? So, and the other graph what we can draw, that is Vx is equals to V naught plus V in by 2. So from here we got to know, this is the first equation. From here we got to know that V naught is equals to 2Vx minus Vi. Now let's draw the graph one by one. Let's take the condition V in is equals to 0. So if V in is equals to 0, that means V naught is equals to 2Vx. So draw the graph of V naught equals to 2Vx. How it will look like? V naught equals to 2Vx. There you go. V naught equals to 2Vx. This graph was for V in equals to 0. Tell me one thing now, where the graphs are cutting? The graphs are cutting at 3 point. Plus V set, minus V set, also at 0. So your output can be plus 5, minus 5 or 0 as well. But I am saying your output will not be 0. Why so? Because this is not a stable state. If I put a ball here, and I give a force to it, I am putting a ball here, I give a force to it. It will pass through this very slowly. It will pass slowly, but it will never settle down on this point, right? It will quickly fall and it will go to this point. So your output can stay at plus 5 Now if your output is moving from plus 5 to minus 5, if your output is moving from plus 5 to minus 5, it can go to 0, but it will go down to directly minus 5. Are you getting my point or not? So when Vin is 0, you can expect only two output, plus 5 and minus 5, not 0. 0 needs to be eradicated. In the negative feedback, what was happening? Let me erase it first. In the negative feedback, here positive feedback was there. In the negative feedback, what was happening? This particular graph, V0 versus Vx, this particular graph was in opposite direction. This particular graph was in opposite direction. The graph was like this. So it was never cutting the saturation voltage unless we increase the value of Vin. When we increase the value of Vin, it started cutting. But for low value of Vin, it never cut. That's why saturation was never achieved and virtual short was valid. Here it is directly cutting these 2 points. Here Vx is not 0. Here Vx is something else. Here Vx is not 0. Here Vx is not equals to 0. Here Vx is something else. That means virtual short is not valid. So that is the reason why virtual short is not valid in positive feedback. So this is the analysis, the exact analysis. I will also tell what is taught in gate. In the next slide we can discuss about that. But this is the exact analysis why in the positive feedback virtual short is not valid. Are you getting this point? Let's check for other points now. Yeah, one more thing we will check. For Vin equals to 0, what did I say? You can have two output, plus 5 and minus 5. Not this 0. You can have two output, plus 5 and minus 5. Let's check in the statistics curve. For Vin equals to 0, what are the outputs you are having? Plus 5 and minus 5. I told you this is dead zone. So in dead zone, you can have two output, plus 5 and minus 5. Let's check for Vin equals to 2. For Vin equals to 2, where Vin equals to 2 will be there? Here. Vin equals to 2 volt will be somewhere here. So again, you can expect two output, plus 5 and minus 5. Let's check that. So Vin equals to 2 volt. What will happen? V0 will be equals to 2Vx minus 2. That means it will cut the y-axis at minus 2. It will cut the y-axis at minus 2. This is Vin equals to 2 volt. 2 volt. Tell me where it is cutting at this point. Here output is plus 5, or at this point here output is minus 5. I think I should increase this line first. Yeah. Here output is minus 5. It is cutting at this point as well, but this line will be eradicated because this is not stable state. So your output can have plus 5 and minus 5. If you are moving from plus 5 to minus 5, it will suddenly go down to minus 5 only. It will not stay at 0. So plus 5 to directly minus 5. So again you can have two output. For Vin equals to 2 volt, again you can have two output, plus 5 or minus 5. Even in the statistics curve you can verify it, plus 5 or minus 5. Now let's check for Vin equals to 6 volt. For Vin equals to 6 volt. For Vin equals to 6 volt, I am expecting only one output, that should be plus 5 volt. For Vin equals to 6 volt, I am expecting only one output, that should be plus 5 volt. So let's check here. So when Vin is equals to 6 volt, what will be my output? That should be 2Vx minus 6. What was this point? This point was minus 5 volt. 2Vx minus 6. That means it should cut the y-axis at minus 6 volt. So it will pass somewhere from here. It should cut the y-axis at minus 6 volt. So it will pass somewhat like this. This point is minus 6 volt. So where the graph is cutting? This graph and this graph. This graph and this graph. Only cutting at only one point. There is no metastable state in this one. It is cutting only at one point, and that point is V0 equals to 5 volt. And what did we see here? For Vin equals to 6 volt, your output can be only one, that is 5 volt. Are you getting this point? By the graphs as well, you verified it. When Vin equals to minus 6 volt, you would expect output to be minus 5 volt only. So again, what will happen? The graph would go something like this. It will start from here and it will go something like this. For Vin equals to minus 6. This will be V in equals to minus 6 volt. This is V in equals to 6 volt. So it is cutting the axis, it is cutting the at this point, and if I increase this line should be increased. If I increase this line, so V in equals to minus 6 volt is cutting at only this point. Here your V naught is minus 5 volt only. That's why when V is minus 6 volt, your V naught is minus 5 volt only. So you are verifying your answer with this hysteresis curve. But before this hysteresis curve, what came? This analysis came. After this analysis, we could go to this analysis. But that was the journey of this analysis, which no one tells. But in the interview, if you tell this kind of analysis, they will be like just very happy with your approach. Also, you can tell them Smith trigger as well. Smith trigger you can quickly draw. You can tell them, okay, it will go like this. What is the meaning of hysteresis? Then you can tell them like, sir, this is also we can verify. And then you can also tell that, sir, here virtual short will never be valid because here Vx values we are getting are always different, not equals to 0. Here Vx is different. Here Vx is somewhat here. So Vx value is always different. Vx value is not 0. So that's why virtual short is also not valid. Got this point? Understood this analysis? And I hope you liked the analysis as well. But let's check one more point where teachers teach how in gate industry it is generally teach why virtual short is not valid in positive and negative feedback. So let's check for negative feedback now. Negative feedback, I will draw a simple OpAmp. And input I can put here. So how do you check negative feedback? What is the rule of negative feedback? Why it is called negative feedback? Let's make a simple control system that you have studied. V in, this is gain A, then output goes, then it comes back and fed back, right? So why is it called negative feedback? Negative feedback means if V naught increases, then we move around the circuit, then V naught should decrease. If V naught tries to increase, there should be some force that will take the V naught down. This is what negative feedback means. That V naught should not keep on increasing. If it tries to increase, there should be some force that takes it down. Let's watch it, let's see it in this circuit. If let's assume if my V naught is increasing, then what will happen? This value will increase. Whatever the value we are having, we call that Vf, that is beta V naught. So if V naught is increasing, this value will also increase. Now what is the value we are having here? V in minus beta V naught. So if V in minus beta V naught, or you can say V in minus Vf. So if this value is increasing, that means this overall value will be decreasing. Now what is my output? My output is this value into A. So if this value is decreasing, that means this value into A will also decrease. Did you understand this point or not? If my V naught increased, this value also increased. If this value increased, that means this value here it decreased. If this decreased, that means further also it is decreased. Say yes or no. Understood? So that's why it is called negative feedback. If V naught tries to increase, it is decreasing. V naught is not continuously increasing. So that's why in negative feedback your circuit is stable. So in negative feedback your circuit is stable. Why so? Because if V naught slightly tries to increase, then it decreases. Are you getting this point? Now if it will not keep on decreasing, now V naught will not keep on decreasing. Now if V naught decreases, what will happen? If this decreases, what will happen? This node will also decrease. If this node is decreasing, that means this node will increase. If this node increase, this node increases, that means the output will increase. So if the output increases, then decreases, then increases, then again decreases, then again increases, then again decreases. So it will go on and output will be stable. Let's see it in OpAmp now. The same kind of analysis we can see in OpAmp. If V0 increases, what will happen? This node will increase. Are you getting this point? If V0 increases, why this node will increase? Because this is like this circuit only, no? Here there is zero current, so no need to make, this is V in. So if V0 increases, that means this node will increase. Now, if this node increases, what will happen? This node will decrease. Why so? Because this is the negative sign. What is our output? Output is A V positive minus V negative. That means if this value is increasing, so this overall value will be decreasing. So your output will be decreasing. So if my output tries to increase, what happens? This node also increases. That means my overall output decreases. Now if my output is decreasing, what will happen? If my output is decreasing, what will happen? This node will also decrease. If my output is decreasing, this node will also decrease. And what is my output? That is A into V positive minus V negative. So if this node decrease, that means this overall value will increase. So my output will increase. So the same thing is happening. Increase, decrease, increase, decrease. So output will be stable. So my V0 will be stable. So basically my V0 will be stable in negative feedback. So that is the reason why system is stable in negative feedback. Now V0 is equals to A into V positive minus V negative. So V positive minus V negative is equals to V0 by A. Now A is very large, A is towards infinity, and this is stable. This is also not increasing, this is stable. It can be a finite value, but this is stable. It is not always increasing or always decreasing. So it is a finite value. So if finite value and A is infinity, that means this value can go to 0. So V positive minus V negative goes to 0. So V positive will be equals to V negative. So that's why virtual short is valid. So this is the second explanation why virtual short is valid, and this was the first explanation. This was the first explanation why virtual short is valid, and this is the second explanation. This is more on the block level. In the previous one we did the circuit analysis. Here we did the circuit analysis, but this was more on the block level. Here we understood the block level. What did we do? We tried to increase V0. Eventually what was happening? V0 is decreasing. If V0 is decreasing, it is again increasing. Decreasing, increasing, decreasing, increasing. That means V0 is stable. So by this simple equation, what we got to know that V0 is my stable. Now V0 by A, V0 is stable, A is infinity. That means V0 by A will be 0. So from there we got to know V positive is equals to V negative. Now let's check for positive feedback. Checking for positive feedback. So we'll make the same circuit. V0. So I hope you are enjoying the lecture. Please do share it in the end once you are done watching, because I am pretty sure in the complete YouTube you will never get these concepts in the complete YouTube. Pretty sure about that. And if you get it, that would be simply a copy. That's for sure. So even in the textbook you will not find these, because these comes after a very much of hard work, right? Yeah, so let's check what happens in the positive feedback. So in positive feedback, if V0 is increasing, what will happen? If V0 is increasing, this node will increase. If this node increases, what is this node? This node is V in plus Vf. This was our Vf. So Vf is increasing, that means Vf is increasing. So overall this value will increase. If this value increases, that means this value into A into this value, V in plus Vf is your output. So if this value is increasing, that means this value will also increase, right? So your V0 will increase. So if I try to increase my V naught, eventually my V naught is increasing only. Now if it is increasing, it will increase more. If it increases more, that means this node will increase more. If this node increase more, that means output will increase more. Then it will increase more, it will increase more, it will keep on increasing, and my output is unstable. Are you getting this point? Let's check in the circuit analysis. If my V naught is increasing, what will happen? This node will increase. And what is my output? My output is A into V plus minus V minus. So if my V naught is increasing, that means this node will increase. Now if this node increases, that means this value is increasing and my output will increase only. So if I try to increase my V naught, my V positive node increases. If I try to increase V naught, my V positive node increased, and because of that, my V naught value increased. So on increasing, it is increasing only. So it keeps on increasing and my output will be unstable. Output will be what? Unstable. And if my output is unstable, that means what I can do, what I was doing in the previous analysis, that V positive minus V negative, that is V naught by A. So A is going to infinity, but this is increasing output, increasing, or it can be continuously increasing or continuously decreasing. It can be both. It can be continuously increasing or continuously decreasing. So I will say unstable output. Why I am saying continuously decreasing? What if I try to decrease my output? So if I try to decrease V naught, what will happen? This node will decrease. If this node decreases, that means my output will further decrease. So if I decreased it, it will keep on decreasing. If I increase it, it will keep on increasing. But in the negative feedback, what was happening? If I increase it, it decreases. Then finally it decreases. If I decrease it, it will increase. So decrease, increase, decrease, increase. That's why output will be stable. But here if I increase it, it will keep on increasing. So basically in positive feedback, what will happen? Like this, like this, like this, like this, like this. It will keep on going. So this is unstable. But in negative feedback, what will happen? Like this, it will slowly die down and stabilize. Well and good. Yeah, so when I teach comprehensive course, at that time I will teach more deeply, but till for now I am preparing you for M.Tech admission interview only. So yeah, this is unstable. So now you can't say that this value will be equals to 0. That's why virtual short is not valid. Virtual short is not valid. Not valid. And in the previous one, virtual short was valid because this was going to 0, but here this is not going to 0. So virtual short is not valid. Why it is not going to 0? Because V naught is your continuously increasing only, no? So you can't comment how large V naught can go. So virtual short is not valid. So here virtual short is not valid, so that's why you can't say V positive is equals to V negative. So this is the second explanation, but the first explanation was this one, which was more intuitive. And from there, we understood the concept of Smith trigger as well. Also, we understood the concept of hysteresis as well. So a lot of concept we have understood here, a lot of new things you understood in just one video of 50 minutes. So yeah, just remember all these things and it will help you a lot in interviews and it will help you stand out from the other guys, right? So yeah, if you found it helpful, please do try to share it with your friends so that they could also know what kind of content is being taught on this channel, on Prep Fusion only. And I am pretty sure no one else has ever taught to you analysis like this and no one will ever teach as well. Okay, yeah. So thank you for watching and yeah, do like the video. Thank you.